Welcome back to our week 9 lab where we'll be studying enzyme kinetics. In the last lab, we worked with the enzyme cellulase type 2 to look at the types of conditions that affect how the enzyme performs. We looked at pH and temperature. So in this week's lab, we will be digging a little deeper into the properties of these enzymes and start understanding a bit more about what happens when we add inhibitors into the system. So before we get too fancy spicing it up with inhibitors, we have to understand how a normal reaction proceeds and the properties of the enzyme that we can measure. So in a normal reaction, we have our enzyme. The enzyme binds its substrate. In this case, we're going to end up breaking down the product or breaking it in half and releasing the products. So the enzyme just binds a substrate and gives us product. The exact site where the reaction takes place and the substrate binds is called the active site. So this anatomy will be important in a bit. So every reaction has a lot of different properties and characteristics that you can measure, but we're going to be talking about specifically 2 characteristics today. One of these is called Km. So Km is kind of a measure of how efficiently the substrate is binding to the enzyme. So we'll see Km is the relationship between the enzyme and the substrate. The second property is called the Vmax, or the maximum velocity. And this is simply how fast an enzyme can go. So I would think of this as kind of like just flooring it in a car. So some cars can go maybe 100 miles an hour at their maximum speed, while other cars can go 150, whatever. So, you know, those big semis that we see in the road, maybe they can go maximum 50 miles an hour. So each enzyme has its own inherent maximum velocity that it can go. So this is a measure of kind of the rate or the speed of the reaction. So we now have 2 properties. We have kind of a way to measure how efficiently the enzyme is binding its substrate, and then how quickly it's going to be catalyzing the reaction once it does so. So these seem like they should be exactly the same and completely interdependent, but we'll see that we can measure them, and they kind of come out a little bit separately sometimes. Okay, so we're used to these types of normal reactions. So what we're going to do is learn about these 2 characteristics in a normal reaction, and then talk about what happens when we add inhibitors. So we'll see what effects different types of inhibitors have on the Km and the Vmax. So let's get started with these 2 properties. So the first way to visualize the Km and Vmax is by using what's called a Michaelis-Menten plot. So I think in order to really understand these plots, it's going to be important that we really get in here and understand what's going on with the axes. Okay, so our independent variable on the x-axis, this is substrate concentration. So this will be how much substrate we allow the enzyme to have. Then we measure the speed of the reaction. So you guys have actually already measured rate in lab. You didn't vary the substrate concentration. This was that same experiment where we kind of measured over time. Okay, and then you guys also had an opportunity to calculate the rate. So this shouldn't be a foreign concept. We've actually done most of this before. So we knew that Km is going to be related to the substrate's relationship with the enzyme, and Vmax is related to the velocity. So that's going to make sense. Okay, so now we know a little bit more about the axis. Okay, here is our actual Michaelis-Menten plot. Okay, so basically collecting samples as we increase the substrate concentration. So low concentration, and we increase it to a high concentration, eventually to the point where we have basically inundated the enzyme with substrate. It has so much that the substrate is just available whenever it needs it, and that's where we can really observe that Vmax. That's kind of like our car analogy. The car can go maybe 100 miles an hour, but if you don't push the pedal all the way down, we're not going to see that speed. So increasing the substrate concentration is kind of our way of pushing that pedal down further so that we can see how fast this can really go at its maximum. Okay, so we can see that kind of happening. All right, so this is just what we've collected. We've not really determined exactly where we can see these two values yet. So let's go ahead and start with the Vmax. So the Vmax is literally the maximum velocity. And so what we're looking for in a Michaelis-Menten plot is this asymptote. So where is this going to eventually go? If we really infinitely increase the substrate, where would this max out? Okay, and so you have to kind of imagine, this is still a little bit far away from the Vmax, but what we'd be looking for is that asymptote. Okay, so how fast this can really go. So you can see some markings kind of foreshadowing down here. The Vmax, I don't think this is a mystery. This is a pretty, I think, reasonable thing to think about. The Km is a little bit different though. So by definition, the Km is the substrate concentration. So it's measured in units of concentration, like millimolar, etc. It is the substrate concentration that is required to make this enzyme go half as fast as it possibly can. So if our car could go 100, what we're doing is looking at the place where it's going 50 and then figuring out what the substrate concentration is here. Okay, so the lower the Km, the less substrate it takes to really get this enzyme going. So that would be kind of a more efficient relationship. Increase the Km, that means it requires more substrate to go half the maximum. So this is kind of the value that we're looking at. Okay, so we have two values here. It will be really important to have a good handle on these. Looking at these types of values on this kind of curve, we can eyeball them. Sure, it's not too hard to eyeball some of these things, but it makes it a lot easier if we have more of a linear system to look at. So let's check out that idea. So another way to visualize the Km and the Vmax is by using what's called a Lineweaver-Burke plot. Okay, and this may look intense, but let's check out these axes. Okay, this is 1 over the substrate concentration. What in the heck? This is not a mystery. Okay, you guys will be varying substrate concentration in lab, so you know what the substrate concentration is. All you have to do is divide it into 1, so we have 1 over the substrate concentration. This is still our independent variable. Our y-axis, this is going to be the velocity. Okay, so again, this is something we know how to measure. Once we've measured it, just take the reciprocal. So this is really not anything to be stressed about. If you can make a Michaelis-Menten plot, you can make a Lineweaver-Burke plot. This is also referred to sometimes just as a double reciprocal plot, just because we take the reciprocal of both of these values. Okay, so again, we're going to be varying this. Our velocity is what we're ultimately going to measure. So why does this make it easier? Having a line always makes it easier because the equations are easy to get and you can really get exact values. Okay, so let's see what's going on here. So in our Lineweaver-Burke plot, the y-intercept is always 1 over the Vmax. Okay, so the Vmax is what we want. The y-intercept, if we know what that is, we can calculate this Vmax value. Okay, so it gets even better than this. The value for our x-intercept is negative 1 over the Km. So remember, Km is a substrate concentration. Therefore, it can't be negative on its own, but we have some negatives here that will cancel out. So our negative 1 over the Km, okay? So when you guys get ready to analyze your data, you'll have data where the substrate concentration is positive, obviously. Unless we're in a black hole, I don't see us having any negative substrate concentrations. But we'll be able to extrapolate that line backwards and get our x-intercept. So this will be our value for 1 over km. And there's even another way to get that km value, and that's by looking at the slope. So the slope is actually km over Vmax. So now we know the slope if we know the Vmax and km, and if we know the Vmax and the slope, we can calculate the km. So this is kind of nice, and really the most useful part of this is that this is a line equation. So we can actually get this equation, y equals mx plus b, and we'll be able to see that our y is 1 over the velocity, so that's our y, equals m, which is the slope. Here's our slope. And our x, 1 over the substrate concentration, plus the y-intercept, so plus 1 over the Vmax. So we'll be able to get this. And the full equation will be written out for you guys also in your pre and post lab assignments. So you'll be able to explore that a little bit more. Okay, so now we know the km, what that's about. We know the Vmax and what that's about. And we know how to visualize them in Michaelis-Menten plot and a Lineweaver-Burd plot. So Km and Vmax, again, are going to be inherent properties of an enzyme and its relationship to the substrate. So every enzyme is going to have this type of relationship with its substrate. So every enzyme has a Km, every enzyme has a Vmax. This is going to vary from enzyme to enzyme, and it's going to depend on what it's doing with the substrate. These values, while they are inherent to the enzyme, that's like our cars, some cars can go 100, some can only go 50. These values can be altered when an inhibitor is introduced. So this is also true for activators, but we're going to be just looking at inhibitors today. So the way that these numbers change is going to give us information about how an inhibitor is interacting with an enzyme. So we'll see that we need to compare what happened with the normal enzyme and the situation with an inhibitor. So in the next video, we'll look at 2 different types of inhibition and how that's going to change the Km and the Vmax.